In this tutorial, I will show you how to generate Python script code for uploaded crystal structure files to calculate either geometry optimization, single point energies, or elastic properties with machine learning MACE interatomic potential. And to do it, we will use this interactive interface, this application. So first you have to download it and compile it. There's another video that I did, which you can find in the description of this tutorial. And basically you have to go to my GitHub link and to the application, and then follow the tutorial here explaining how to compile it. And also in this other video you can see how to use my application to run directly calculations within this interface. But if you wish to run some like more computational demanding simulations that you expect will be running for several hours or even days, it's better to generate the Python code and run these simulations directly in the console. Otherwise, it's possible if you use this interface, since it's a web-based browser application, you can face probably some time disconnections, errors. Okay, so to generate the Python code, I will suppose you have this application already compiled, and to use it for the Python code, first I need to upload again my crystal structures here. So I prepared some example structures which I will upload here. For instance, these four. And then I can select which foundation model I want to use. So just to calculate it very quickly, I will use the smallest one, the fastest one also, and I will use calculations on GPU. And to use this, I need to accept these uploaded files and also log them. And now I can select which calculation type I want to do. So let's start with the energy one, just single point energies. And I can now directly go into this start calculation tab and generate the Python script. So then I can simply download this script, save it, and I can open it, copy its content into console. So I have this I have prepared these folders for each different type of calculation. So let's go to the energy, and I will remove all the content from here. So now it's empty. So I will create the Python script file into which I will copy all the content, save it, and now I can run the script. And also, before I will run the script, I need to make sure that I activated the Python virtual environment with installed packages that are necessary also for this application. And the packages are mentioned in the requirements, but you will automatically install them if you follow this tutorial, and then you just need to activate this virtual environment also into the console field that you want to run this Python script simulation. So I needed first to activate this environment, so that I would do if I go to this folder where I compile my this application, and then I would let's just source the path to it, and in my case it's MACE and bin activate, and I would activate this virtual environment with this command, or I can just, it's not activated, so I can activate it with this. Okay. Yeah, and now I can run the command, the Python script. So just initially it will take a few seconds to start, and then you can see all the information about the calculation in the output. And when it's finished, you can find the calculated results in table. So if I go to this energy, okay, the optimized structure is empty because I run just a single energy calculation, but I can find here this table where I have the name of the file and then the energies and also formation energies. Also, if I want to just quickly preview, I can see these charts comparing the formation energies for each file, the relative energies compared to the lowest energy state, and comparing also the total energies. Okay, so that is single energy calculation. And now I can show you also the geometry optimization. So let's go to this folder first. I will delete all previous calculations. So now it's again empty, and I will prepare the Python script. If I go back to the settings, I will just switch this mode, geometry optimization. I can modify these parameters. So for instance, instead of optimizing both the atomic positions and the unit cell, I can optimize only atoms or only the cell. Also, I can choose if I want to optimize only certain directions, or if I want to fix the angles or also optimize the angles and some other parameters. So just now, to be quick with the calculations, let's select some worse settings. And okay, let's have it like this, and we'll prepare the Python script. So okay, it's generated. It's generated. So now I can download it again. And for me, the easiest way how to put it into the console is just to open it and copy the content, create new file here, copy it here, and save it with Ctrl S and exit with Ctrl X. And now I can run it. You can see that I don't have here the uploaded crystal structure files, and that is because this script, the generated Python script, will automatically create the uploaded structure in postcard format. And also, one thing that can be important is that if you upload a postcard structure here and you have selective dynamics, so you want to fix certain atomic positions or certain atoms in just certain directions, this geometry optimization or this generated Python script will take these constraints into account. So they will be considered, they will not be erased if you have selective dynamics in your input structure postcard file. And I have it here in one of my example file. So if I just show you, you can see that as for instance, I have here two fixed directions and one fully fixed atom. So it will be preserved during the run. So let's just run it now. few seconds before it will initialize. And now it's running, so you can see here it started with the file that have this selective dynamics options there, or constraints inside. So it preserved them, and you can, during the run, you can observe the console. And after each file is calculated, the result folder will be updated with the information basically about it, like the initial energy and the energy after the optimization, and the initial lattice parameters and the optimized lattice parameters, etc. Okay, yeah, that was quick. And so let me show you the results. And now I have here the optimized structure in postcard file, and I also have here like the trajectories for each step, geometry, the ionic step during the optimization, and I can just illustrate to you if I put it into the animation, so I can see how the atoms evolving during the geometry optimization run, and also how the lattice is changing. Okay, let me stop it. Then I have here some information about the results of the geometry optimization. So most important is probably this CSV file, where I can find all the necessary information that I would probably want. So name of the structure, then the initial energy, and then the energy after the optimization, the initial lattice parameters, the lattice parameters after the optimization, and yeah, the change of the lattice parameters. This another file, it's a shorter one, and it contains more like the settings, but you can also see here the initial energy, the final energy, and also the formation energy here. And yeah, and then automatically, just to quickly preview the lattice parameters changes, I can see this chart showing how each lattice parameter change from the initial value to the final value in percentage for each structure, and the lattice parameters A and B and C, not the angles. Okay, yeah, so that's the geometry optimization. And now let's go to the last one, which the Python code currently supports, and that's the calculation of elastic properties. So I'll remove everything from here again, and let's generate the file. So just simply change the settings here, the calculation setup, and you can generate a Python script. Okay, copy into console. And now I can run it. So this will calculate all the elastic properties like the bulk modules, Young modules, etc., and also all the elastic constants. And the last option, that for the Python code, it's currently not yet fully functional, but you can use this interface to calculate it, and it's the calculations of phonon properties. So you can also do it here. Actually, I can show you. Let me do it for one structure to be quick. For instance, I'll do it for this alpha titanium. Let's select phonon calculation, and So, okay, this is finished. I will show you the result soon. But meanwhile, I will start this. Start calculation. You can observe some information in the console if you want. And it's finished. So I can go to results, click the phonons, and I can see how the phonon dispersion curves looks like along certain main K path direction, and also the density of states. And I can generate here like the temperature analysis, so I can see how the entropy is evolving, free energy, and heat capacity. Okay, so just this illustration. And now let me show you the results for the elastic calculations. So this is again empty, and results. So I have here separately the elastic constants in one table. You can compare them if you want. Then I have here like for each structure separately, and overview, it's here. So here you can find the bulk modules in different formulation, shear modules, Young modules, Poisson ratio, also density you can see here, longitudinal velocity, transverse velocity, average velocity, Debye temperature, and certain approximation depending on the elastic constants if the crystal structure is stable or not based on the elastic constants. Okay. So yeah, that's all. How to use this interactive application to generate the Python script that will perform these three types of calculations within the console for a larger number of structures that you want to simulate at once and then compare them with each other, for example. Okay, thank you for your attention. And if you spot any bug, you can also let me know on this email address. And yeah, I hope this application will be useful to you. Thank you.